Welcome back, children. In the previous video, we talked about the Ampere circuitous law and we also employed it to find the nature of the magnetic field inside and outside a current carrying conductor. I have to tell you something about the application of the Ampere circuitous law and what you have to be careful about when you try to apply this law. I want you to understand that. Okay, so what does that law say? It says that the closed loop integral B dot dl over an open surface is equal to mu naught into I, where I is a current which is piercing through that surface. Okay? Let me focus on this integral now. Okay? I can write this integral like this. I can remove the vectors. In that case, it will become b and cos theta and then dl. So b dl cos theta. This is equal to mu naught I. Okay. Now b can be a function of L. So what it means is that if you have chosen a path in such a way that B is changing with the distance from the current, if it can be a function of L, so you don't have a constant B in magnitude. Okay, so B is one value here and B is of another value here, another value here. So it can be, B's can be different. So B's are a function of length. So if that is the case, BL and then cos, again cos, the theta can also be a function of L, because like at some distance the theta could be small, maybe here the theta could be something else. So the theta can also be a function of L over the path. So in that case, f of L and then dl is equal to mu naught I. If you end up in a path like this, if we end up with the path like this, then I cannot take anything out. I have to integrate them all together now. There is no constant which I can take out of this. So I will integrate them all together, then whatever I have would be equal to mu naught I. So that's not very useful to me. But if I find a path in such a way that B remains constant in magnitude over the entire path, then I can take B out. Then I can take B out and then do the integral here. So this integral may give me some value x or something, okay, and say this is equal to Bx, and that I know is equal to mu naught I. So this integral has given me this value, and I also know these two values. Now I can find B. But to find B must be constant along that path in magnitude. That's a very critical idea. If B is not constant along the path of your choice, then you can't use this law, Ampere circuitous law, profitably. It cannot make your life easier. So this is a point that you have to remember. In this video, so we are going to talk about the magnetic field inside a solenoid. A solenoid is a pipe-like structure. Solen in Greek means pipe, and oid, you know that it's like. So metalloid, metal-like, cuboid, cube-like. Likewise, solenoid is pipe-like structure. It is like a spring, okay? It's like a slinky, like this. So you have a current carrying conductor which is made into this shape, like a spring. So current enters from one end, and then it travels through the solenoid and then leaves at the other end. So a solenoid is like a pipe-like structure. Now we are going to find the magnetic field inside the solenoid, and we are going to use the Ampere's circuitous law to do that. Okay, let me take a single circle, because a solenoid has so many circles combined together. So let me just take a single ring. Okay, if I take a single ring, and if I see it like this, if I see it in this fashion, if I see it like this, then if I cut it up, and I'm just seeing the cross section of that, okay, this is one end, and this is the other. Okay, this is how you see it. Like you can imagine a circle, half circle here, and another half circle inside the board. Let's say that the current is coming out like this from this end, and the current comes out and then goes into the circle this way. So the current is coming out, and here the current is going in. So you can imagine this, I hope. Okay, it's like the ring, one ring of the solenoid. If you have it like this, what would be the magnetic field inside this circle? Okay, so clearly at the center it will go straight, and then there will be lines like this, and field line will be like this. Likewise, field line will be like this side. Okay, and maybe like this. So this is how the field lines are going to look like inside the circle. And if you bring another circle near it, okay, let's say I'll have this. Let me try to complete this one. Okay, but this time I'm going to draw dotted lines now. I will check. This is how you complete the circle. Now let me take another circle now, another ring. So this is another ring. Again, half circle on this side, half circle on the other side. So here too, so this is coming out, it's going in. Okay, and how would the field lines be here? So they will be the same. Here also, we'll have a straight line at the very center, and then we'll have things curving, and then things curving, and something like this. Okay, and same here. Okay, something like this. So if I have one more, the same thing happen. Okay, I am not going to do it. But you can imagine that all these circles will have magnetic field like this. So if you bring them together, then what happens is that, like they join. The field lines will be something like this. Something like this. Okay, so if you have lots and lots of terms, and if you bring them all together, then ultimately this will produce a magnetic field like this. Okay, if I have infinitely long solenoid with a small radius, so then inside the field is going to be like this. Okay, and then you will have conductor here, the circle here, circle, very close, very close, very So in all this, at the top the current is coming out of the board, and at the bottom current is going into the board. Draw some lines. Okay, so it will become straight, and we can clearly see that if I have this kind of an arrangement, which is pretty long, then the field values will be same on each line. So the B will be constant throughout the diameter or the area of the solenoid. But what will happen outside? What will be the field lines will be here? Okay, I'll have a field line here, but then this will also have bigger and bigger circles that will also try to cancel it. Okay, so this will put some circles, and then this, they also will put some circles in the opposite direction. Okay, so clearly what will happen is that this will be the direction of the field due to this part would be in this direction, but this would be in this direction, so they'll try to cancel. If the diameter or the radius of the solenoid is small, then clearly if we take some distance here, notice that the field set up by this part will be almost equal to the field set up by this part. So as we go further away from the solenoid, this will become weaker and weaker and weaker. That you can see clearly, because the current on the top is in this direction, the current at the bottom is in that direction. So the field at this point will be trying to cancel each other out. And the farther you go, the moment this distance becomes negligible compared to the distance at which you are trying to find B, then you can expect the field to be close to zero. And if you have an infinitely long solenoid, you can pretty much treat that the field outside is zero. You'll have field B inside, but you'll have field, but the field outside will be zero. You wouldn't have any field here, and the same thing will hold good for this too. So B here is equal to 0, and then B here is equal to 0 there outside. But you have an infinitely long solenoid for this to happen. When you have an infinitely long solenoid, then the lines inside will bring it closer and closer, so you become pretty straight, very straight. Then you will have a constant value here, but outside the field will be 0 on both sides of it. Okay, both here and here, the field value is 0. Now you need to find the value of B. So how do you find the value of B? That's the question. That's what we are going to do now. We are going to use, once we understand this, we will find this B. Because this understanding is critical. You need to understand how the field lines of a very long solenoid would be. Okay, the length is much greater compared to the width. In that case, this will hold good. Okay, so I hope you understand the magnetic field lines in a solenoid. If you do, then we'll proceed to employ Ampere's circuitry law to know the value of B inside. Okay. Okay, what kind of surface am I going to assume? To apply the Ampere's circuitry law, you need an open surface, and then you have to do a closed loop integral of it. So what kind of surface am I going to find to do that here? I'm going to apply this kind of a surface. You see, this is like a solenoid, and if I take this sheet of paper, okay, like that, this is the kind of surface I will use. A part goes in, and then there's a part outside. That's what I'll do. Let's see. If you imagine a surface like this, I'll say this is A, this is B, this is, I'll say this is C, this is D, this is E, this is F. It's point. Okay, just outside. And A, B, C, D, E, F. Let me traverse in the same direction. Like I'll do it here. I'll make the loop in this direction. I'll start from A, go to B, to C, then to D, then to E, and then to F, then to A. So that is how I'll come back. And now this is the open surface. Why did I choose this kind of a surface? For one thing, the current must pierce through the surface. So if I have a ring like this, then if I take a surface here or somewhere else, the current is not piercing. So I am just taking a surface through which the current goes. Okay. So you see how many piercings you have. If I is the current which is flowing through this, then you see 1, 2, 3, 4, 5, any number of circles. Okay, times the current I. So I. So many I's will be through the piercing through that surface. Okay, just as I showed you using the spiral binding like this. Okay. Let us say that this coil has n turns. The total number of turns, n is equal to the total number of turns. Okay. And let's say n is equal to the number of turns, total number of turns divided by the length L, where L is the length of the coil. Okay, so it's pretty big compared to the radius of the coil. So this will give you the number of turns per unit length. So N by L will give you the number of turns per unit length. And I assume this surface. Let us suppose that this length of the surface is small l. Okay? Then, how many turns are there? Then the number of turns in length L is equal to n times L. I'll use it later, but you can understand that if n is equal to capital N by L, which is the number of turns per unit length, then the number of turns in a particular length L can be found by multiplying L with n. So we'll come back to it later. Okay. So I'm going to do this integration. I need to start from here and then I need to do a closed loop integral of B dot dl. And that must be equal to mu naught times the total current piercing through the surface. The first one, I need to do the integral, right? The closed loop integral B dot dl. Okay? I'll do this. Is this equal to, I'm going to split it up. I'm going to do the integration from, I'm going to start from A, I'm going to go to B, from B to C, C to D, D to E, E to F, and F to A. So this is equal to, I'll do the integral from A to B. What is the field value B here? It's B, right? It's constant, the same at every point, because it's a straight line activity, and it's constant too. So it's going to be B dl. Okay, B dl. So I'll say B dot dl. We'll do it. Plus then B to C. then B to C. Again here the same B, and then this is DL in the direction. The direction is perpendicular now, we'll come back to that. And then C to D. C to D here, my B, there is no B, I told you, like outside the solenoid there is no B. So my B will be 0, not DL. There is nothing there. And then I go from D to E. This is D to E. Again my B here is 0, not DL. And plus E to F. E to F. My B is again 0. B outside is 0, dot DL. Plus F to A. F to A. Now closes the path. There I have B dot DL. So now that is the closed loop integral of this open surface that I assumed. So this is the surface, then the closed loop integral of this open surface. The surface is open, but then this integral, this, they become the closed loop integral of this open surface. That is what we have done here. I can ignore this 0, this is gone. I can ignore this 2, this 0, this is gone. I can ignore this 2, this is also gone. Then I need to worry about these three now. Okay, first then I will be left with A to B, B dot DL plus B to C, B dot DL. So I'll do it this way. Okay, let me expand it straight away. So B dot DL, first A to B, B dot DL. B is in this direction, DL is also in this direction because I'm traveling in this path, right? So DL is also in this direction, so that is BDL. Cos theta is 1, they are in the same direction. But here again, BDL, now cos B is in this direction, DL is in this direction, so cos 90. Then plus here F into A, again BDL. Now what's the cos theta now? B is in this direction, DL is in this direction, so the angle again is cos 90. So this will also become 0, this will also become 0, so I am just left with integral B dl A to B. Then what would I get now? B into dl from A to B is what is that length? The length L. So BL. Okay, once I get this, I'm going to equate it to mu naught I, right? The mu naught into the amount of current which is piercing through this surface. So my integral, the closed loop integral B dot dl of this open surface has given me B multiplied by this L. So I'll do it here. So B L, that's this integral, the closed loop integral B dot dl is equal to mu naught into the total amount of current which is piercing through the surface. So I total. But what is I total? Mu naught into, okay, for one turn I have I. And how many turns are there? There are n times L turns. So NL into I. That is my total current, the amount of total current piercing through the surface. So that is equal to BL. I can cancel L and L here. So I am left with B is equal to mu naught N to I. Okay? So this is the magnetic field inside a solenoid. This is B inside. Inside a long solenoid. Okay. In this case, the radius of the solenoid R is much less than the length. Okay. So, which is equal to B. B is equal to mu naught N times I. So we've used the Ampere's circuitry law to calculate the magnetic field strength inside a long solenoid. And this is how we do that. Hope you understand this. Now let's calculate the field inside a toroid. A toroid is a solenoid which has been joined end to end in the form of a circle. So a toroid will have this kind of section. Imagine a circle here, and then the toroid would be like this. So that you are going to find the field inside the toroid. Okay. I didn't get the toroid exactly, but I will draw it now. But you can imagine that to be a solenoid which has been joined end to end in the form of a circle. So this would be the toroid. So this is a toroidal structure. Okay. So I'm going to find the field inside the toroid and outside. Outside the toroid and this place and also here. So let me call this as a this I'll call it as A. Or I'll put it this way. Okay, I'll call this as P, this I'll call this as Q, and this side I'll call this as S. Inside is S. Outside, there are two outsides. One is P, another one is Q. Okay. First, let me try to find the field here inside in the region P. So what I'm going to use the Ampere's circuitry law here also. So what I'm going to do, I'm going to come up with my open surface. My open surface is again a disk, a circle, you can say, like this. Okay. So if you want to find B at this point, then let's see like what's going to happen. So I'm going to, let's suppose that I have B1 here. Then B1 dot dl. I do a closed loop integral of that, and that must be equal to mu naught into I. This is about region P. Okay, I have this surface here, the imaginary surface, which has my point of interest B as a point on the boundary. So what I'm going to get now? What's the current which is piercing through this surface? There is no current that is piercing through this surface here. If there is current, it will go only in the toroid, in the windings of the toroid, but not here. So mu naught I is 0. So mu naught I is 0, mu naught into 0. So this is going to be 0 anyway. So the integral B naught dl will give me 0, and because there is no current which is piercing through this area, through this open surface. By symmetry, B1 must be the same here, because there is no preferred position. You see, this B1 is affected by these turns and also by these turns in the same way as B1 here would be affected too. So if B1 is here and B1 is this, here too, and B1 must have the same value along the surface. So if I take that B1, and what should I have? So if you have the center, and this is going to be R, so 2 pi R, which is equal to 0. When can this be 0? When either when R is equal to 0 or B1 is equal to 0. R cannot be 0. So only B1 has to be 0. So we say that B1 is 0. So the field in the region P of the toroid is 0. There is no magnetic field in this region within the toroid. When I say within the toroid, the other outside of the inside of toroid. Okay, it's like this. In this region, it is 0. Okay. The next one is Q. I can employ a similar reasoning here. In the region Q, the other outside region, again I'll say this is B2. This point is B2. Let me imagine this as the open surface. This is the open surface. So Q, this is B dot dl again. So that is going to give me mu naught into I. Then what is the current which is piercing that surface? Okay. So if I do this, what's the current which is piercing? The total amount of current. Look here, both this part and this part will pierce the surface, right? It's both of them. So as this pierces the surface and this also pierces the surface, current goes in and current comes out. So one is positive, the other one is negative. So the total amount of current again that is piercing this surface is also 0, because when you have those rings, the ring goes in and then the ring comes out. So I positive, I negative. When you sum it all up, then it becomes 0. So this is going to be mu naught into I minus I. Okay. So I will call this as a total bit. Okay. I minus I. So, and then if there are n turns, then you will get this n. Anyway, in any case, it is going to become 0, because the net current which is piercing the surface is 0, because the amount of current that is piercing and going in one direction is going to be balanced by the amount of current which is piercing the surface and going in the opposite direction. So this is 0. Again, I'm going to use the same rationale. So this is going to give me, I'll call this as B2. B2 is there, but let's say this is this radius. Again, I'll call this as R2 or something. I'll call this as R2. Okay. That's R1. I think you can understand this. So this is going to, because of symmetry again. See this point, if we take, then all these lines, all these currents will produce a magnetic field in the same way as they would do it for another point here. So B2 must be the same at every point along the boundary of this region. So that would be 2 pi or 2. They are equal to, this multiplication is equal to 0. R is not 0, which means that B2 must be equal to 0. So there is no B here too. The magnetic field here, the outside the toroid, is also 0. So there are two outside regions of the toroid, and in both the regions, the inside-outside region and the outside-outside region, in both the regions, the magnetic field is 0. But what about the region S, which is inside the toroid? The inside. Okay, it's like this. Inside this toroid. How do we do that? Again, I'm going to come up with another surface here. So this surface is somewhere in between. So this is a toroid. So this surface ends somewhere here. Okay, so it's like that. It doesn't come out, but it is inside this toroid. So you can see that only this current, only these, this part of the toroid is piercing. The wire is piercing the imaginary surface here, not both sides. Only this is piercing, because the surface is inside. So all these things must be piercing through the surface. So again, if we come to S, the region S which is inside, then I'm going to do B3, I'll make call it as B3. Okay, B3 dot dl is equal to mu naught into the total current. What's the total current here? Mu naught into, how many are there? If there are n turns in the toroid, capital N turns in the toroid, and each turn has I, then this will be n times that I. That's the amount of current which is piercing this surface, open surface. Okay? Then B is in this direction, then DL is also in the same direction. They make the angle between DL and B is 0, so cos theta will be 1. So BDL, again, B must be the same at every point, right? Because B has to be the same because of symmetry. This B must be the same as this B, because this B is going to be affected by everything else. The same way this B is affected. Okay? So you get B3 into this 2 pi, maybe, R3, I'll say. Okay? R3. This will be R3. This is not 0 now. So now B2 is equal to mu naught Ni by 2 pi R3. And this is equal to mu naught I into N by 2 pi R3. But what is 2 pi R3? Okay, I can the surface can go from here to there. Okay, yeah. So I can take the average radius R, and if I take the average radius R, then N by 2 pi R gives me the number of turns per unit length, because 2 pi R is the length of the boundary. So you get N by 2 pi R. So this I'll call it as N. Okay, this will be called as N, the number of turns per unit length. So B3 is equal to mu naught N I, and this has the same result as the solenoid. So this is how you will use the Ampere's circuitous law to find the field strength inside and outside a toroid. And we have seen 3 examples now. One is inside and outside a conductor itself. Here you are finding the magnetic field using the example in the previous video. And today we have seen the application of Ampere's circuitry law to find the magnetic field inside and outside of a solenoid and also a toroid. Hope you understand this. Okay, now we will do example 4.9. Let me read the problem. A solenoid of length 0.5 meter has a radius of 1 centimeter and is made up of 500 turns. It carries a current of 5 amperes. So what is the magnitude of the magnetic field inside the solenoid? So this is a problem. We can see that the length is 50 centimeters. So the length of the solenoid is 50 centimeters or 0.5 meters. And the radius is 1 centimeter or 0.01 meter. So you can see that the radius r is much less than the length. It's like it's 50 times greater than the radius. So we can use a long solenoid formula which we have just derived, which is B is equal to mu naught n I, where the small n is the number of turns per unit length. Then what is n? N is equal to number of turns per unit length. So total number of turns divided by the length of the solenoid will give you the small n. So capital N is 500 and this L is 0.5 meters. So this is going to be 1000. Okay, turns per meter. So it's 500 turns per 50 centimeters, and obviously you will get 1000 turns per meter. So that's the number of turns per unit length. So you found that. Now it is only a question of a straightforward substitution of these values in this formula. So B is equal to mu naught is 4 pi to 10 to the power minus 7, and the small n is 1000, and I is 5 amperes. So many Teslas. Okay, so what you get here? You get 20, 4 and 5, 20 pi, 20 into 10 power 3 into pi, I'll write 3.14, 10 to the power minus 7 Tesla. So 10 power 2 into 10 power 4, 10 power minus 7. So 2 into 3.14 into 10 to the power minus 3 Tesla. So you get 6.28 into 10 to the power minus 3 Tesla. So that is the field strength inside the solenoid. So this is not a difficult problem, it's a very simple problem, a straightforward application of the formula and the numbers. So the only thing that you need to pay attention to is this part, because radius is much smaller than the length. Then you can use this formula. If the radius is not negligible, or the radius is comparable to the length, then you cannot use this formula. For example, like if the solenoid is of only say 2 centimeters or 3 centimeters long, then clearly you cannot use this formula. But the solenoid has a length of 50 centimeters, so the length is much greater than the radius. So you can use the long solenoid formula. So we have just done that. Hope it's clear to you.